welcome to lecture series on advanced linear algebra. We have already seen in our last lecture what is unitary operator, what is unitary matrix. We have seen over a finite dimensional inner product space, the unitary operators form a group with respect to multiplication compositions. So, based on that principles, if I consider, let UN denote set of all n cross n unitary matrices, then UN is also a group with respect to multiplication composition. This means if A and B belongs to UN, then A into B also belongs to UN and A inverse also belongs to UN. And since each unitary operator is also an isomorphism, so this implies that A inverse, which is equal to A star, an adjoint of the A, also belongs to UN. So, all these properties of the group also holds good in UN. Based on this concept only, we shall proceed and we shall utilize this concept to prove some interesting results. So, let me consider a nice problem. Let A be a n cross n invertible complex matrices, then my claim there exists a unique lower triangular matrix say capital M such that the entries on main diagonal is positive and L into A equal to U is a unitary matrix, So, what I want to say you, if you consider any n cross n invertible complex matrix, then there exists a unique lower triangular matrix with the characteristic that each entry on the main diagonal are positive number and L into A equal to a unitary matrix. So, let us give the proof of these results. So, the proof of this result is based on basically Gram-Schmidt orthogonalization procedures. If you recall how one has to translate, one has to get from a set of linearly independent vectors to a set of linearly independent orthogonal vectors by using Gram-Schmidt orthogonal procedure, then you will see the proof is very simple. At least for the existence of the lower triangles, and the uniqueness has to be also proved separately. So, let us see how to prove this result. Given A as an n cross n invertible matrix, let row 1, row 2 and row n of A be denoted by beta 1, beta 2 and beta n respectively. Let using Gram-Smith orthogonal procedure, the corresponding orthogonal vectors are alpha 1, alpha 2 and alpha n, where for 1 less than equal to k less than equal to n, the set alpha 1, alpha 2 to alpha k is an orthogonal basis for the subspace say Wk, which is spanned by beta 1, beta 2 and beta k, and the kth orthogonal vector alpha k is given by beta k minus sigma inner product of beta k alpha j by norm of alpha j square into alpha j equal to 1 to k minus 1. So, we know this Gram-Smith orthogonal procedures, that procedure says that the kth orthogonal vector will be of this form. So, this implies one can write down alpha k as beta k minus, since a linear combination of alpha 1, alpha 2, alpha k minus 1 is a vector in the subspace of W k. So, we will be able to express this vector as a linear combination of beta 1, beta 2, beta k minus 1. Consequently, there will be k minus 1 constants, say ck1, ck2, ck minus 1, such that this expressions can be written as sigma j equal to 1 to k minus 1 ckj beta j. So, one can express alpha k like this. What is the motivation behind considering this? My aim is that I want to write down the given matrix as a product of a lower triangular matrix and an unitary matrix. So, based on that only I am rewriting this structure. So, this implies if I consider alpha k by norm of alpha k will be equal to beta k by norm of alpha k minus sigma j equal to 1 to k minus 1 ckj by norm of alpha k, and so now consider a unitary matrix capital U whose rows are alpha 1 by norm of alpha 1, alpha 2 by norm of alpha 2 and so on alpha n by norm of alpha n. So, that each of them will be orthonormal, magnitude of this vector will be 1. So, I have considered a unitary matrix U, which first row is alpha 1 by norm of alpha 1, second is alpha 2 by norm of alpha 2 and so on. And let me consider also consider a matrix say capital M defined by where mkj this is equal to 1 by norm of alpha k minus ckj for j less than k, and this is equal to 1 of norm of alpha k for j equal to k and mkj equal to 0 for j greater than k. So, the way I have considered the row mk kth row of the matrix A capital M, so certainly mkj will be give me a lower triangular matrix, and which main diagonal entries are, if I consider main diagonal entries mkk, these are basically 1 upon norm of alpha k. This implies we are having alpha k by norm of alpha k equal to sigma mkj into beta j, j equal to 1 to n. So, I can write down this kth row of the my capital U, which is equal to like this. So, this implies I will have capital U equal to capital M into your capital A. So, this means that there exists a lower triangular matrix capital M such that U equal to capital M into A. Now, this capital M is also invertibles, we will prove it later on. So, that we can say that A will be equal to M inverse U, but anyhow. So, before going to that part, so first I have to show that this M is unique. Claim capital M is unique, unique. Suppose not, suppose not. Let T plus N denote the set of all n cross n lower triangular matrix whose entries on main diagonal are positive. This means that each of the lower triangular matrix is invertibles. Let M1 and M2 be any two elements of T plus N, I mean set of all the lower triangular matrix with the property that main diagonal entries are positive. Let M1 into A belongs to UN. I mean to say this set of all n cross n unitary matrix. Also M2 into A belongs to UN. I am saying there are two lower triangulars say M1 M2 such that M1 into A also belongs to UN and M2 into A belongs to UN, means both M1A and M2A are unitary matrix. Claim M1 must be equal to M2. Since M1A belongs to UN, this implies M1A into M2A inverse belongs to Un, because M1 is also unitary, M2A inverse also unitary. So, the product will be also unitary. So, therefore, M1A into M2A inverse will belong to Un. So, this implies M1A A inverse M2 inverse belongs to Un. So, this implies M1 into M2 inverse belongs to Un. Friends, I am not going to prove that one nice results that T plus n, that is set of all the lower triangular matrix with the diagonal entries are positive, they form a group with respect to multiplications. That part I am leaving on you as a homework. You can check it. Those who have done the group theory, definitely they will be able to do it. So, you can also check, please. So, based on that, I will assume that T plus n is also group. So, here T plus n is also a group with respect to multiplication. As a result, this implies M1 and M2 inverse also belongs to T plus n, and M1 into M2 inverse also belongs to T plus n. I mean, since M1 belongs to Tn plus and M2 also inverse also belongs to Tn plus. So, therefore, the product of M1 and M2 inverse will be inside the T plus n. So, M1 M2 inverse belongs to Un implies M1 M2 inverse, the adjoint also exists, and that will be equal to M1 M2 inverse inverse, again it will be in Un, please. So, this will be again Un. So, this is also belongs to your Un, and this is also belongs to T plus n as well as T plus n. So, but we know the adjoint of matrix is transpose or conjugate transpose based on real or complex, transpose or conjugate transpose of the lower triangular matrix lower triangular matrix. So, it will be an upper triangular matrix. So, a matrix, this implies what? This implies M1 into M2 inverse is upper as well as lower triangular matrix. This is upper as well as lower triangular matrix. So, this implies that M1 into M2 inverse is a diagonal matrix, with diagonal entry are positive. This implies, since this U and U star is equal to identity. So, this implies that an M1 into M2 inverse into M1 M2 inverse star is equal to identity. This implies that the diagonal entries must be equal to 1. I can say plus minus 1 is 1, and however, positive entries in diagonal confirm that the diagonal entry must be equal to 1. Okay, since we have seen that M1 M2 inverse into M1 M2 inverse star is identity. So, this implies that diagonal entry has to be plus minus 1, but since the diagonal entry is positive, this implies that the diagonal entry of M1 M2 inverse certainly will be equal to 1. So, this implies that M1 M2 inverse equal to identity matrix. So, this implies M1 equal to M2. So, we see that this implies that there exists unique lower triangular matrix capital M such that U equal to M into A. So, this implies the diagonal entry must be equal to plus minus 1, because if you consider that M1 M2 inverse is belongs to the unitary matrix, then certainly M1 M2 inverse into M1 into M2 inverse transpose has to be equal to identity. So, this implies that diagonal entry must be equal to plus minus 1, but since the diagonal entry of the each M1 M2 inverse is positive, so this says that diagonal entry of M1 M2 inverse has to be exactly equal to 1 only. So, this implies M1 M2 inverse equal to identity matrix. This shows M1 exactly equal to M2. So, we see for any n cross n complex square invertible matrix will have a unique lower triangular matrix such that the lower triangular matrix into that given matrix will be called to an unitary matrix. These results can be utilized but with more general sense. We will discuss this issue in our next class.